Frequently, it's useful to prove uniqueness of a particular value or number. For example, let's assume that I have the equation ax plus b equals 0, where a is non-zero. The claim here is that there exists a value z satisfying the equation, and z is unique. That is to say, there is one and only one value that satisfies this particular equation. Okay, so how do we prove a claim like that? Well, the first step is to show that there is a value satisfying this equation. So how do we show that there is a value z that satisfies ax plus b equals 0? Well, we solve for x. So we subtract b from both sides, and we divide by a, which we can do because a is not 0, and we get x equals minus b over a. So if we set z to be minus b over a, then we'll see that z does satisfy this equation. That's what we just showed. Now we need to show that z is unique. What does that mean? It means we need to show that for all, let's say, m, such that am plus b equals 0, i.e. m is some other solution to this equation, we need to show that this implies m equals z. So that means that z is unique. I mean, this basically says that for any other value m that satisfies the equation, it actually turns out to equal z. So z is a solution, and it's the only solution. How do we prove that for every m such that am plus b, how do we prove that for all m that satisfy this equation, m equals z? Well, we just use some math. So we have, we pick any value m that satisfies this equation. We know that am plus b equals 0. That means that am plus b also equals az plus b, because az plus b is also 0. Z is a solution. Now we can subtract z from b from both sides, and we get, this implies that am equals az. And here again, dividing through by a, which is non-zero, so divide both sides by a, we get that m equals z. We didn't do anything difficult, but it's important to note that what we did do is we took an arbitrary value m that satisfied this equation, am plus b equals 0, and we showed that m, through a sequence of steps, must equal z. So again, z was a solution, and for any other value m that satisfied this equation, we showed that m must equal z. So z is the unique solution. Another useful strategy for proving things is often working backwards. So take this example. Say we want to prove that for all x and y, the arithmetic mean, namely x plus y over 2, is always greater than or equal to the geometric mean, namely square root of x, y. And let's assume that x and y are both greater than or equal to 0. So taking the square root is going to make sense. Well, it's not immediately clear why this is true, but let's manipulate it a little bit. So the first thing we might just want to do is play around with this equation. Let's get rid of the square root sign. Those are often pretty ugly, and let's square both sides. So we'll get x plus y squared over 4 is greater than or equal to xy. So this first line implies the second line. And it's also important to notice that if you started here on the second line, x plus y squared over 4 is greater than or equal to xy, you could move backwards and you could conclude the first statement. These two statements are equivalent. The first one implies the second one, and the second one implies the first one. So we can move in between these two statements in either direction. Okay, so now we're down to this second statement. Let's multiply both sides by 4. X plus y squared is greater than or equal to 4 times xy. Once again, this statement here implies this statement, but also if you started here and divided by 4, you would get this statement. These two lines are equivalent. Okay, so let's expand this. X plus y quantity squared. What is that? Well, it's x squared plus 2xy plus y squared. And again, we have greater than or equal to 4 times xy. This statement implies this one, and this statement implies this one. We've done just simple, they're equivalent. We've done simple mathematical manipulations. Okay, now I'm going to subtract 4xy from both sides. So we'll have x squared minus 2xy plus y squared is greater than or equal to 0. Once again, I could move forward from this step to this step, or move backwards from this step to this step. Okay, and now I can factor this left side to the quantity x minus y squared, and on the right-hand side, I have something that's greater than or equal to 0. And finally, not to repeat this too many times, but I could have moved from this statement to this statement. This implies this, and also this implies this. The reverse direction is 2. These two statements are equivalent. Now look at the last line. X minus y quantity squared is greater than or equal to. This is obviously true. All right, clearly true. Why? Well, any number squared is always greater than or equal to 0. X minus y is some number. I'm squaring it, so it's clearly true that it's greater than or equal to 0. Okay, but then that implies that this step is true, and that implies that this line is true. That implies that this line is true. That implies that this line is true. And that implies that this line is true, since every two lines were equivalent. So we started from something that was true, namely x minus y quantity squared is greater than or equal to 0, and we show that that implies exactly what we were trying to prove, namely that x plus y over 2 is greater than or equal to the square root of xy. So we took what we wanted to prove, we massaged it via some simple mathematical manipulations, and we got to something that was clearly true. Then we were able to work backwards and get back to a step that we wanted to prove. Now, sometimes you can't work backwards. So for example, let's say I had 3z was greater than or equal to 5. I don't know, I'm working some step in my proof and I get 3z is greater than or equal to 5. And then I multiply both sides by 0. So I get, which is, it implies that 0 is greater than or equal to 0. Okay, but how do I go backwards now? It's not clear exactly what to do. I have 0 on the left-hand side and 0 on the right-hand side. But I can't multiply both sides by 5. I can't multiply both sides by 3z and get back here. I can't add 5 to both sides and get back to this step. I can't add 3z to both sides and get back to this step. So while it is true that 3z is greater than or equal to 5, does imply that 0 is greater than or equal to 0 because I can multiply both sides by 0. That's a step that I can't reverse. And if we had a step where we multiplied both sides by 0 during this proof, then we wouldn't have been able to work backwards.